So we will move to the next presentation, which is intelligent prevention of machine downtimes. This presentation is being presented by Jan Birod, who is a product owner for digital services in Bosch, and Alex Tolev, who is the solution architect manager in AWS. The floor is all yours, Jan and Alex.
Yeah, thank you very much. So I will give you today a brief introduction of how Bosch Rexroth tackles the digital transformation towards fully connected manufacturing. For all those who don't know, Bosch Rexroth, we are one of the global suppliers for industrial automation and drive technology. And we are running basically everything starting from small tooling machines up to complete steel mills or steel manufacturing plants, whether it's electric or hydraulic. And today we'll give you an introduction of how we generate data on the manufacturing level and how we generate therefore benefits to our customers. On the next slide, so as we start our journey, we first of all ask ourselves, what are our customer requirements? So as I already said, we have a broad application base. Most of our customers are lacking more and more hydraulic know-how, so they do not even know how the components work in detail. They have from time to time no machine insights at all. They often need to operate 24/7, especially for automotive or mining or metallurgy applications. It's quite important to run the systems with a high reliability. They even have a high downtime costs. So in case that their application has a stillstand, it costs a lot of money. And especially mining applications are facing the issue that they're having lost long distances to travel to this application. So somewhere in Chile or in Australia, you from time to time have to travel roughly 1 day even to go there, and without knowing what's the issue, what do you have to do for maintenance case. And as we have a global service department, they are striving for a reliable partner, which we then offer as additional service, so that we also do the field service in combination with digital service portfolio. If we're looking on the machine lifecycle, we have an area of optimal machine condition. Then there is some point in time where you reach the optimal maintenance period. Afterwards, you will have a power loss of the components of some critical parts, and then sometimes somewhere in time there will be a downtime, whether planned or unplanned. We tackle this with 3 theses. We have 3 packages as a basic to start. We have a monitor, just an overview of what is happening. We have our maintain package to give more insight of what happened. So in case there is a power loss, a filter locked, performance issues, it's a more rule-based approach to identify in case there is something happening. And then we have our premium package with predict, where we offer what will happen, where we detect on machine learning or condition-based analytics, how is the behavior of the component and what's necessary for the customer to change. So whether it's a pump, which reaching their life cycle time before a power loss happens, or even detecting failure of some sealings or whatever you could imagine there. If we look on the cycle or our journey where we start, we set our baseline with a new standardized products. So focus in the first step was focus on the technical proof of concept. So build up a first connectivity stack, prove the business case, and bring the product into the market to validate, okay, we can generate benefits for our products and gain benefits for our customers. Afterwards, in the second step, we handed over to modular products, so more variants, function enhancement, and modularization. We focused ourselves to develop the product or our digital service in a modular way so that we can adapt it to every combination of our products. To give you a feeling, we have roughly 3 million different products which we offer every year to our customers with pieces of one time per year up to 300,000 pieces per year. So there's a huge modularization and variance in our product portfolio, which we tackled in this second step. In the third step, we focus on systems and applications overall. So it's more a holistic approach where we then scaled our analytics and improved our analytics on a complete system level. So for example, on a steel application, where we then analyze the complete drives during this whole production cycle. But you do not always need to have predictive analytics. We also made some basic analysis, as we call it. You can see here is one of our standard products, which had an average oil temperature around 28 degrees, and our system automatically detects that this is not a normal condition. So we there performed or give our customer the advice to deactivate the cooling and check the new state. And now the oil temperature is around 55 degrees, which is an optimal optimal condition. And only with that one example, we saving roughly 7.2 million liters of cooling water every year, because they just do not need the cooling for this application. When we are talking about predictive analytics, and we have a customer application in a cement mill where we detected an anomaly because of some small damage in the pump before an error occurred. So we were able to inform our customers, recommend him some spare parts, and plan the maintenance with him. And we saved we can change the pump without any unplanned downtime, so that our customer could perform at his best level. I mean, if we are talking about all this, how do we cooperate with AWS? So as we started, we made a first proof of concept where we get in touch with AWS expert. We had an architecture review where we get insights of how to best use AWS, how to use the services, how to combine them, how to build the architecture. We often did this in the last few years, so there's always a review, always some insights, how to improve your architecture. We as well have a combined go-to-market strategy, so that we are getting support from AWS to how to enter the market, which could be a good place to step in, and just make calls like this today to show what we are doing, what is Rexroth offering, and how all our customers can benefit from our solution. What we also did during especially the last 2 years, we had a development support, so that AWS ProServe in special supported us during our development, because we had a huge lift and shift plant where we needed more capacity, and then we had a cooperation to develop to lift our application on AWS for enlarging our services with a new feature, which former was located on a local server and now is running on AWS. Well, that's basically all from my side, and I would hand over to Alex to show more about what we are technically doing, how the architecture looks like, and what our technical approaches are.
Thanks, Jan. Thanks for the sum up. Hi everyone. My name is Alex. I'm a SA manager with AWS, and I've supported actually Jan and Bosch Rexroth journey on exactly the intelligent predictive maintenance actually of machines. I'm going to talk a little bit about now the technical side of the solution. Not going too detailed or too deep into the technical aspects. Nevertheless, I want to give you a glimpse of an understanding what was important, what kind of decisions were made, why those decisions were made during this journey. So first of all, let me share you a high-level view on where we agreed on to have some kind of a layered domain architecture, meaning that you can see we have 3 layers. When we start from top to bottom is the front-end external services layer, where really applications, web applications, user interfaces, external parties, as well as devices can access actually the second layer, which is the API layer. And the API layer has publicly available APIs and redirect actually the request then back or down to the domain layer. So the domain, as you can see, is consisting really isolated bounded context in terms of a specific or single use case. For example, you see the domain data lake as well the domain application. And one key feature, one key aspect we wanted to have upfront was really to make this architecture evolvable and extensible over the time. That is the reason why you see, for example, a domain XXX. And you will see that in the next slide, that we can apply similar concepts or similar services and structures for upcoming domains in the future when, for example, there might be a new business case or a new feature we want to include for the overall package for the customer. Now, turning it a little bit into some beautiful icons of AWS services, you see the same layered domain approach as you have seen before, just swapping it actually in a horizontal way, just because of space in a slide. Following the same layer domain approach, you see on the left-hand side the front-end external services layer, where, for example, user interfaces such as Grafana, as well as the machine learning pipeline, the web application UI, or external services based either built on AWS or devices are accessing the second layer, which is the API layer, such as the Grafana API or the data API. And then on the right-hand side, you see exactly that principle or that architecture pattern where we said, okay, we want to split that up into different domains, for example, the data lake domain or the application domain. What is common across the API and the data lake domain is that both are working with APIs. So we are leveraging Amazon API Gateway there with an AWS Lambda function in the background. And they are responsible for actually routing the requests to the respective domain with a private API, such as the Data Lake API or Application API, again, leveraging here Amazon API Gateway. A similar concept then you can see with AWS Lambda functions is really to have the read and the write requests routed to either Amazon Kinesis data streams to store the data then with Amazon Kinesis data Firehouse into Amazon S3, or to write the time series data into an Influx DB cloud. Also in the application domain, which I will touch a little bit more into detail, is you see Amazon DynamoDB here with two different aspects. One is the event store, and the other one is really the view store, where we leverage Amazon DynamoDB's capability to store all the events as some kind of an appendix or an appended log, as well as to have an Amazon DynamoDB table as a view store to fulfill the read requests. Now, I talked a little bit already about some architecture paradigms we have used in the application. Nevertheless, I want to really focus on 5 aspects. First of all, as you have seen, it's a complete serverless application bounded with or complemented with a SaaS solution, the Influx DB Cloud one, because that was the key thing to say for the architecture to remove the undifferentiated heavy lifting of operation and maintenance, and really that the developers can focus on the valuable tasks and to provide business logic. That is the reason why in the architecture you see a lot of AWS Lambda functions, as well as Amazon API Gateway and other serverless services from AWS. The second paradigm we have used is the command queue responsibility segregation. What is CQRS, just to recap that for the ones who don't know the pattern or the paradigm here. Usually when you have applications and you want to have some kind of a persistence layer, you have a data model, and usually you have some kind of a CRUD data model where you create, read, update, or delete the state of your data in your persistence layer. We have chosen a different approach because we said, okay, we really want to decouple both. Meaning that whenever some write events came in, this is the so-called command. With this command, we actually store this event into the Amazon DynamoDB event store. And whenever a read or query comes in, we have a separate storage layer, the Amazon DynamoDB view store, to retrieve the data and to push it then actually to the front end or an external services layer. Why is that so? Because we wanted to have really a decoupled fashion in terms of what is being stored, in terms of events being stored, which might be used for reproduction of in case of failure or something like that, with the queries or with the data which is used to be read from the API layer or from the front end and an external services layer. Also, a common or known paradigm backend for front end. You saw that every single user interface application is leveraging a specific API, which is also then routed back to the respective domain. So with authentication mechanisms, authorization mechanisms as well in place. Event sourcing, I already mentioned, in combination with CQRS, we really receive the events and store them in a log, which is appended. And so we have really the raw data in there and don't only change the state of a model, but really are able to reproduce the full flow or the full log actually in case of a failure. So that was also really decoupling a lot, or having that kind of decoupling in the architecture. Last but not least, API driven. So we have everywhere we're using APIs. Either it's a publicly available API or a private API with, again, authorization and authentication mechanisms in place. Now, I mentioned that the architecture is completely serverless or with some SaaS offerings, and I want to touch base a little bit on the point why the decision was made for Influx DB. If you remember, in the data lake domain, the time series database was preprocessed and stored by an AWS Lambda function in Influx DB, and there was really the discussion about, okay, why not leveraging as well Amazon Time Stream? So what we did before I jump into the data points, why this decision was made, it was really a collaboration again with the customer, so with Jan's team as well, with me as a solutions architect and with the Amazon Time Stream service team to understand the full requirements. And then to do some kind of an exploration phase to see, okay, how can we support the queries which are written, what kind of best practices do we have with Amazon Time Stream. And there are there are two aspects actually where, from a best practices approach, we decided then to go with Influx DB. First of all, it was a discussion about leveraging multi-measure records versus single measure records. The time series database is really great, and you can store with both, with Influx DB and with Amazon Time Stream, both of those records. Nevertheless, Amazon Time Stream performs really well if it comes down to multi-measure record, because the data scanned and the volume is reduced and can leverage really aggregation functions even better. So that is the real intention of, or the main purpose of Amazon Time Stream there. Together with the so-called scheduled queries to write exactly those aggregation functions and to receive the data out of it, there was the decision made again during this exploration phase that it would take an additional effort for Jan's team to implement that in a timely manner. And as always, time is tough, and we had a tough timeline. We had to make a decision how to proceed. Again, with the great support of the service team, with the great support of Jan's team, we came to the conclusion that this additional effort is currently not feasible and not possible. And that is the reason why, as well, from a cost perspective, not maybe potentially leveraging Amazon Time Stream in a best practices way, that was the situation why a sound decision was made for Influx DB. The good thing is, what I want to showcase is really that customers should always choose the right tool for the right job. And in this case, this happened, and Jan's team is super happy with that decision. And so that is, and their customers are as well happy. So I think that is a win-win situation. With that, faster as expected, I'm done with my part, or with the overall presentation, and I think we have time for Q&A.
Thank you, Alex. Thank you, Jan, for this presentation. I think we have a question in the chat. Praveen, do you want to come off mute and then ask the question?
Yes, yeah, thank you. So for us, it's not so. First of all, we have cloud synced time base on every of our edge devices, where we manage that they are all in the right, that they all have the right time. Beside that, we do not compare the different systems or applications with each other. So therefore, it's for us not that important to have them all in the same or that they all are time consistent. And for
Yeah, I could think of some use cases.
Sorry?
Yep. Yeah, I think I was going to say that there are some use cases where we have to sync the time. For example, if you have some video coming off the manufacturing floor and you have other metrics which are coming off the machines, and then you wanted to find out when that happened, what was the steps done at that time, then you may have to sync the video with the data which comes off the machine, right? Otherwise, you're saying there is no use case for you to sync time between the different sources.
Actually not, no. Or the devices or the complete application is in one, is acquired with one time stamp anyway, and then we have the time consistency for this application or this manufacturing line.
Okay. I had a question in that development journey that you had in, I think it was slide 4, where you spoke about the different stages of development, like you create some proof of concepts, then you do functional analysis, and you do get the scaling. Customers who are embarking in this journey, what timeline that should they expect for these different phases? If they all, I'm assuming they will also go through the similar phases when they start implementing it. Do you have any rough timeline how much it takes to reach stage 3?
Yeah, so I would say it's a quite hard question. It depends on the one hand on the capacities you have. So if you have a development team of 100 people, that's something different. If you only have 5, that's the one point. And on the other side, it also depends on how many different variants you want to tackle. How is your already installed base, or how are your products? If you already have very digitally sized products, as we heard today, a lot of connected cars and all the technology which is already there, I think the timeline from a single component to the whole system can be 1 to 3 years, depending on the capacity you spend and the complexity you want to handle. For us, it took roughly 3 to 4 years because we have a very tough complexity. So that's just to give you a feeling. But as I said, it's quite hard to estimate.
Thank you. I'm just looking at the chat if there are any other questions from the audience. Somebody wants to ask a question. Mute now. One last question from my side, and then we can move on. Typically, in this kind of manufacturing implementations, one of the requirements we typically get from our customers in automotive is that the manufacturing plant should work even if the connectivity to the rest of the world is lost, the internet is lost. So in those kind of cases where you have to think of resiliency, how do you approach that? Do you have some components in the plant and then in the cloud kind of thing? How do you approach resiliency in that case?
Yeah. So we have two points there. First of all, the PLC or the system control or application control is running independently from our digital service. So we do this additionally to the real automation system of the automation system of the application. And the second topic is that we store on a local base and make a local pre-processing of the information, so that in case of an interruption of the network connectivity, we store up to, depending on the size, 24 hours to 1 week of data, and then transfer it into our system. So that it's the application is running without our service, but to ensure that the information is processed and analyzed afterwards, we store it locally to get known this. And we also have implemented some automations that in case of downtime of an application, which should not be down, so if we do not receive any information, we reach out to our customer to get insights, because you can really good measure it if the application is running on full power and then no network or no data is coming anymore. There's not a normal behavior. So that's where we then directly interact with our customers.
Thank you, Jan.